Hello everyone, my name is Konstantin Vladimirov, and welcome to the 14th lecture of the Master's course in C++ at MIPT. In the first part of this lecture, we spent quite some time building intuition about ranges, iterators, sentinels, and views. We mostly focused on what they are and how they behave. Now, in the second part, I'd like to slow down a bit and start asking more uncomfortable questions. Not so much how things work, but why they are designed this way and what consequences follow from these design choices. Let's start with a simple comparison. In the first case, we have a vector of integer, and you can see it here, it's vector v, and we use ranges find to search for a value. Nothing unusual here. In the second case, the situation is almost the same, except how now we have a vector of structures. They still want to find element with value 4, but this time it's stored inside a field. So instead of comparing elements directly, we compare a projection of each element, and conceptually, these two cases are extremely similar. And that naturally raises a question. In the first case, we use ranges find. In the second case, we end up using ranges find if to project something here. It would be nice if we could use like the same mechanism in both cases, just by providing some projection. And in other words, can we somehow turn a projection into a view? Can we use our lightweight view as a projection? And that's the idea we are going to explore now. So, what do we do if we want to use find but with a projection? We already know one possible answer. We can project the whole range first. Here, we take our range of S, and instead of searching in it directly, we build a transform view over it. This view exposes only the X field of each element. Now the range looks like range of integers, and suddenly ranges find works exactly the way we want. So instead of saying find with a projection or find with a predicate, we are saying find over a projected range. And this raises two important questions. First, who remembers or can guess what std_memfn actually is and why we need it here, or we don't? And second, much more interesting, how would we implement transform view internally? Because on the surface it looks trivial, but as we'll see next, the details really matter. And let's recall the structure of the transform view. But before doing this, let's look into this std_memfn. Let's look at the example. And actually, in this case, let me show you the godbolt. Yep. And actually, in this case, we don't need it. You see, we do have something here like ranges find if, and we do have something here like ranges transform view. And if we will check, all tests are passed. But what if I will just, in this case, remove the memfn entirely and only field pointer remain here? Let's try. And as you can see, basically nothing changes. Let's wait for compilation, couple of minutes. Why nothing changes? Nothing will change here, nothing will change there. Because in this case, yes, nothing changed. Because in this case, we are working with standard transform view. And standard transform view addresses this field via student voc. And studMemFan is a way to wrap the field if the view is obsolete or poorly written or so on, to isolate this callable from use of student voc. With studMemFan, you can just call it via the regular braces operator, and it will call student voc underneath. Okay, now when we talk a bit about studMemFan, and I will remind you when we will need it. Let's deep dive into stud transform view. And please pause the video now and think, how would you structure stud transform view? I believe you did it. 3, 2, 1. Okay. At first glance, it looks almost trivial. We have an underline range, we store a callable, and when someone dereferences the iterator, we just apply that callable to the element. And I hope this is not the design you came up with, because if this is the case, then now you will need to think once again. Seems easy. Yes, this seems really easy and nice, but this naive approach hides a problem. And if you also just mistaken like this, please think again. How would you improve this? Do you have any objections? 3, 2, 1. And of course, the transformation function, this f, is not necessarily cheap. It may have state, as we already seen in the lecture on lambdas. It may capture something. So instead of storing the callable inside the iterator, it makes much more sense to store it in the view object itself. Then, the iterator only keeps a pointer or reference back to the view and uses callable from here, like parent f of starbase. And look, here where we do need our studMemFan, because in my poorly written transform view, I just was lazy. I haven't write student voc here, and boom, without studMemFan, everything will explode. And in poorly written template code, in obsolete legacy template code, you will often see something like this, and in those cases, studMemFan will help you. Okay, and okay, and I'm using this field from the parent class. And this looks like a very reasonable design choice. At least iterators now are cheap. Iterator stores only iterator for range and transform viewpointer. We reduce the size of the iterator, we avoid copying a potentially heavy function object, and everything still seems to work exactly the same. So far, so good, but the real question is, does this design choice have any consequences? That's what we'll look at next. How do you think? And of course, so here is the unexpected consequence. Because transform view stores a pointer to itself inside its iterator, it no longer model borrowed range. The iterator doesn't stand on its own. It always refers back to the view object, and as a result, once the view is destroyed, like here in this case, this iterator is ranges : dangling. And all iterators obtained from single view immediately becoming invalid as long as view became invalid. And even if the underlying range is still alive, this happens because to call function to transform, we need to refer to view, not to underlying range. And this is not an implementation detail. It follows directly from the design. So now let's look at which ranges actually do model borrowed range, because it is important. First of all, don't forget the simplest case. Any L value range is a borrowed range, period. If something is an L value, it lives longer than any expression before it dies. If I take a transform view and store it in a variable, in this case, I will take this transform view, store it in a variable, everything is great. Nothing dangles. Next, there are several ranges and views which are never, which always model borrowed range, no matter what is underneath. These are ref view, subrange, empty view, and iota view. And okay, no matter what is underneath subrange or ref view, they are independent of details. Subrange do not store pointer for subrange in iterators over subrange. Yes, iterators over subrange are iterators over the underlying range. Uh, and it doesn't matter what they wrap, they just never dangle. And then there is a whole class of views that model borrowed range only if the underlying range is borrowed. For example, common view, you may remember it from earlier, that's one where the iterator and the sentinel have the same type. The same applies to owning view, to reverse view, to take view, drop while view. Anything that models borrowed range, common view on it also models borrowed range. So in practice, the set of borrowed ranges in the standard is actually quite small. We have like 4 unconditionally borrowed and like about 10, including one exotic, that are conditionally borrowed, and others are not borrowed ranges anywhere, anyway, in any cases. And why? And because they are behaving just like this transform view. And whenever we talk about this kind of behavior, where a range reaches into itself in its iterators, takes some stored functional data and applies it lazily during iteration, this is very often referred to as lazy behavior. That term will come up again and again. But is it really lazy behavior? And here is where things get a bit subtle. Let's say we sort a range using a projection. We call ranges concol sort, we pass a comparator, and we pass a projection, for example, extracting age from person. Now, something interesting happens. If we already had a view built on top of this range, that view is now sorted as well. Why? Because the view doesn't store any data of its own. It just keeps iterator into the underlying range. So when the underlying range changes, the view immediately reflects that change. And let me show you this example. I believe it is really enlightening example. Okay, let's go for it. Yes. What do we do here? We do here studio actor views transform to X, and we expecting 1. We changed underlying thing, and now we are expecting 3, and total is passed. So view just stores at iterators, nothing else. And every time we access the view, we are effectively reobserving the underlying data in its current state. And now the obvious question is this really lazy behavior in the classical sense? Because why is it lazy? If on any attempt to retrieve the data, we just calling the function again and again and again, we are not lazy. We are really busy. Nothing is being postponed until the first access. Now, nothing is being computed once. Instead, the view is constantly rechecking the underlying range and pulling values from it again and again. So I don't really like calling this lazy behavior. I prefer a different term here. I usually call this hesitant behavior. The view is never sure what's underneath it. every axis is a fresh question. What does the range look like right now? And this hesitant behavior is exactly what drives many of the design choices we've already seen, especially when it comes to borrowed ranges and dangling iterators. Okay, and let's go a step further and talk about filters. We start with a stud vector, then build a filter view, and then transform view on top of it. Yeah, great. So, what do we get? We filtered everything that is less than 5. So we basically left in our range everything that is less than 5. This is 1, 2, 4, and 3. And now we transformed it, just multiplying by 2. And we do have 2, 4, 8, and 6. If this is not obvious, please stop the video now and study the example until it will be obvious for you. And by the end of this lecture, we'll stack quite a few of these things together, and here's the idea. We take a vector, apply filter view, we apply transform view, and everything looks straightforward. And of course, this filter cannot be a borrowed range. If we create a temporary filter view and immediately call find on it, the iterator will get back dangle. So now let's think. In order for this to work, how would you implement a filter view? Please pause this video and try to design how will filter view look like. Try to write it on a sheet of paper, maybe. 3, 2, 1. And I believe you did it. And let's start as usual with something simple. We define a filter view of an input range and unary predicate, and we doing everything like in transform view. We are storing range here, base, we are storing predicate here, we do have some iterator, and begin returning iterator need to skip all elements that are filtered out before it reach real begin, before it reach real first element. So, in begin, we just call ranges find diff on the base range. That sounds reasonable, but think about what this means. Every time you call begin, you may have to walk over the entire underlying range again, and that's not allowed. The standard very clearly requires that begin is amortized big O of 1, big O of constant. This requirement is unconditional, so this naive implementation is simply non-standard conforming. And let's think how we will fix it. I hope you did. And yes, when we are hearing the word amortized, we probably cache something. And instead of recomputing the beginning every time, we compute it once and store it. Yeah, lazy behavior. Lazy is here. Now we are lazy enough. On the first call of begin, we are caching this find if, and this is amortized or big O of constant. And if it is already cached, we're just returning it. Doing real work once when caching the result is fine. So we add an optional cached iterator, and our filter now stores the base range, the predicate, and a cached begin iterator. And things are getting a little heavier. And also, we are losing something really important. Now we see the real problem. Because the filter has to modify itself during iteration, a const view over it, this is const view, may lose iterability. You just cannot cache anything in const view, because caching anything in const view means altering the const view, which is prohibited. This const We create a vector and create a filter view, bind it to a const variable now we call begin, and suddenly it fails. Let me show you. I believe this is the example. Yep. Okay. So everything looks okay, but passing const ranges at this argument discards qualifiers. And what do we want here? This is really scary. And of course, if I will remove const anything, everything will be fixed. And it's not just filter view. The same behavior appears in drop view, drop file view, split view, reverse view. In C++23, it is also in chunk by view. All of them cache begin. So by fixing wide requirements, amortized off or big O of constant for begin, we end up losing iterability for constant views. What a mess. And the new chunk by view I mentioned on previous slide is actually quite interesting. Here we take a vector and group adjacent elements based on a comparison predicate. Here we go. In this case, the predicate is ranges less, so elements are grouped while the sequence keeps increasing. So 1, 2, 3 are grouped, and now 1 is less than 3, so we are chunking this. 1, 2, 3 is first group, 1, 2, 3 is second group, 3, 3, 1, 2, 3. And this chunk by view is, as a result, we don't get fixed size chunks. We get runs that depend on data itself. So instead of slicing by indices, we are slicing by structure. And now let's look at next two examples. Here we have slide view and stride view. At first glance, they look similar, but both somehow reorganize the range, but they do very different things. Slide view gives you overlapping windows. Stride view skips elements. And this is where it becomes tempting, so just stare at the code and try to predict the output. Pause the video, take a piece of paper, and actually work through this example step by step, because views like this are exactly where all the things we discussed today, sentinels, cache, and constant iterability, suddenly become very real. And if you don't think about them carefully, they will happily surprise you. So please try to predict this output. Next, click on this link and check yourself. Great. And now it's time for a difficult conversation. This is where we really have to talk seriously about the pool model. This is pooling from last lecture. Do you remember it? Because this hesitant behavior when views keep pooling values from each other leads not only to caching and loss of constant iterability, it leads to something much more subtle. Let's look at a classic example. We have two functions E7 prints E and returns if something is even. Square prints S and returns square. And let's see it on the Godbolt. Great. Now let's wait for a moment before we feel yes, we are got it. Great. So we are building two views. First view is transform view over filter view. Filter view is a 7, transform view is over square. So we are filtering even numbers and then squaring. And in the second case, we are squaring and then filtering. What do we expect to see on the screen? And of course, if we first filtering and then squaring, we're expecting to see check for every element and square for filtered element, yes? And if we transforming and then filtering, we are expecting to see squaring for every element and filtering for every element. Let's try. Let's look at the real output. And in the first case, we see even, square, even, square, even, square, even, square. Perfectly fine. First case works as expected. Let's look at second case. Square is even and now square again. Square is even and now square again. And now is even. And now square, square is even, square is even, again, square. What is happening here? It looks so it looks so ineffective. What's going on? Why this happens to be okay, and this happens to have a lot of unnecessary squarings? Look, we have a proper number of even checks. Is even here of 0, is even here of 1, is even here of 4, is even here of 9, is even here of 16. It's proper squares of numbers, 0, 1, 2, 3, 4, and so on. But for every check for even, we have 2 squarings. What's happening? What's the reason? And let's focus on this case. What do we do here? What do we see here in terms of behavior? The filter wants to decide whether the current element should be kept. To do that, it has to pull a value from the transform. So the transform calls square. Now the filter positions its iterator, but then we later dereference that iterator. And it has to pull the value again, and which means calling square again. So for the same element, square may be executed twice, which is completely unobvious from this because we use unknown owning and we use them here. Do you expect here square to be called twice? And if square is really heavy, what will you do? And this is not laziness. If anything, this is over-eagerness. You might ask, wouldn't it be better the filter cache the value? And the answer is sure. Sure, cache the value in the filter, all the values. But then you'd be caching everything. And at that point, most of you probably would say, no thanks. We will not caching everything. It will be really ugly design decision. So this is trade-off on the pull model. You need to check if pull model works and try to keep your predicates lightweight. And now let's look at something even worse. We built a filter of a simple vector. We filter odd numbers. So far everything is fine. And nothing wrong here. And now we iterate over the filtered view and modify the elements. We iterate over filtered and modify the elements. And boom, now odd elements became even elements and vice versa. Then we iterate over the same filtered view again and modify them once more. And this is undefined behavior. And this is really nasty undefined behavior. The vector ends up in completely unpredictable state. Let me show you. Here we go again. Yes. And here we filtering out. And vector now is 4 and 10. And we are adding 1 and ranges copy. And adding one more and again ranges copy. And what we will see on the screen. And we see 2, 4, 8, 10, 3, 4, 8, 10. Isn't it great? So I mean, I mean, how this can be, how this filtered range can output like this. And yes, it can. It can even more. And why is this? Because the filter view is built on top of caching. And on top of the pool model, it assumes that the underlying range does not change in ways that affect filtering. Once you violate that assumption, all bets are off. This is exactly the kind of UB that the range standard makes explicit. And the practical rule here is very simple. If you build a filter view, you should treat the underlying range as effectively immutable. If you want to modify it, throw the view away and build a new one. Otherwise, you're very likely to hurt yourself and badly. At this point, you might reasonably ask, okay, but what was all of this for? Why do we need those views, please? Take it away. But the answer is for this beauty on this slide. Because now, if you don't mix up filter and transform, and if you don't accidentally step into UB, you can finally write code like this. Instead of deeply nested view constructors, or even worse, for loop with an if inside, you can write a pipeline. We start with an stream view, we pipe it into a filter, then pipe it into a transform. This read left to right, it matches how we think about data flowing through the program. And quick question, just to keep you alert, does the resulting var model borrow range or not? How do you think? Don't answer now. Make investigation in home and write this in comment. Not just yes or no, but why or why not. The answer must be more than 4 words. You guess why. So, how does this actually work? The rules are surprisingly simple. You can write this form like view constructor of range and arguments. This form func of arguments of range, and this form range pipe func of arguments. All three forms are effectively the same as long as func returns a view. If you have a view, you may call view here, view here, view here, pipe it with range. This is a mental shift. Instead of calling filter view on a range, we treat filter as something that adapts a range. And the pipe operator is just syntax for applying that adapter to the range on the left. Now here's an important subtlety. Look at these two expressions. In the first case, we directly construct a filter view. In the second case, we use this strange thing. We use filter. We use home filter. From the user's point of view, A and B are hardly distinguishable, but their status is completely different. Filter view is just a function, but views filter is a special kind of function object that supports piping, supports composition with operator bitwise OR, and this kind of object is called a Niebloid, named after Eric Niebler, one of the early range evangelists. And for this to work correctly, a Niebloid, this one, must inhibit argument-dependent lookup. Why? Because otherwise, unqualified lookup plus ADL will produce extremely surprising behavior. I'm not going to dive into the exact standard tricks used here. I left it for you for open investigation. But just important takeaway for you. Views filter is not just a function. It's carefully designed adapter object whose whole job is to make pipelines work correctly and predictably. Pipelines will not work or will work poorly with this one. And that's what enables the entire range pipe syntax. And just to show you an example, which is, I believe, slightly instructive about what happens. You see, this is the essence of problem. think about this namespace and think about those classes and this function foo. And now we do have our Niebloid function with overloaded operator braces and some concepts on it, like in this case it is enable if. You may rewrite it in requires as you wish. And now this is inline context per swap, which is a Niebloid object of this type. And now let's go ahead. So we do have this MyStud. We do have this swap, which is inline const expert in this namespace S6. And MyStud B, A and B, foo of A and B. And foo of A and B will be 1 because it is here. But now when we are using namespace S6, MyStud A, C and D, and foo of C and D is now 2. And please think, how is it possible? If you dig in this place, you will learn something new about name resolution. And for students in this audience, I will probably ask this question on my exam. Okay, before we dive into more details, let's pause for a moment and look at something practical. We already know how to write our own views. Now it's time to learn how to write our own range adapters to compose our own great pipelines. And the good news is writing adapters is slightly easier than it might seem. If you were frightened by the previous slide, please don't afraid. Nothing is scary because standard library have some facilities for you to not think about ADL exclusion and such. In fact, very often the best way to write our own adapter is not to write a new one at all, but to compose existing ones. And this example, taken from Tristan Brindle's talk, I wholeheartedly recommend it, and it will be in my bibliography. And let's take a very simple, very realistic task. We want to trim white space from a string. Leaving white space, trailing white space, trim all of it. And after thinking for a bit, we might come up with something like this. First, we define a generic trim over a range. Generic trim is trim back composed with trim front. And now what do we have here? We have trim string over string with this generic trim of any range composed with toString. So first trim and then convert to string. And we need to write this code. We need to write internals of all these functions. And so far it looks perfectly reasonable, but how do we actually write trim front and trim back? And you see, pool model isn't always bad, because pool model makes trim front obvious. At the very least, we can express both operations using existing views. And trim front, what is it? It is range piped with drop while. Views drop while, with this is space, just drops everything from the beginning of this range, and we are reading left to right, yes? It drop everything from the left of this range while something is space. Great. Trim back is slightly trickier, but views unknowing they are lightweight. We reverse the range and this costs us nothing. We just changes begin to R begin and end to R end. And we drop white space at the front and reverse it back. And yes, this uses the pool model, it involves views stacked on top of views, but in this case, it's actually fine. Reverse view is extremely cheap. It doesn't move data. So overall, it's reasonably efficient. The real question is a different one. Do you like the reference semantic of the result? And now comes a nice part. Once we remember that views drop while is itself just another adapter, we can stop writing functions that take ranges at all. Instead, we can work purely with adapters. Our trim front just returning this adapter. And trim back reverse, pipe trim front, pipe views reverse. Result of this pipe is just another adapter, not range. Trim back is function that returns an adapter, so basically it is an adapter. And trim is just composition of trim front and trim back. And at this point, trim string becomes beautifully simple. Pipe the string into trim. Then pipe the result into toString. And this is exactly the styles ranges were designed for. Small composable adapters connected with pipes, doing one thing each, readable, reusable, and once you get used to it, surprisingly elegant. I think this example is like surprisingly elegant, but we can do it even better. And we not yet know what is toString. Yes, let's write it. Let's start with a simple version. Just write toString function, and toString function over any view is a really simple one. Please pause this video and think how you will write this function over any range. And I think it is not a problem for you, but just to keep you alert. 3, 2, 1. Okay, let me show you the good boat. You will be surprised if you failed to do it in 5 minutes, because it is really simple. Yes, any range by the range definition do have begin and end, and toString have a constructor from begin and end, and this constructor requires 2 iterators, not iterator and sentinel, which is perfectly fine because we do have common view and we are adapting our range to be common view and then constructing toString out of it. Isn't it nice? It is. We do have some vector, we are filtering it, we are dropping it to string, and we do have string AC. Because, yes, because we we dropped any odd chars. Okay, great. So we just made it comment and then we constructed the string. Great. Now that we know how this toString works, let's make the beautiful version, an adapter. And what do we want? We want this to work. We want to work stud vector is7 and s is the pipe views filter is7 pipe toString. And what exactly is to str? What is its official status in the language? It's not a variable, definitely. It's not a function in usual sense. It's something that participates in piping. So it must be some object with an overloaded operator. And something that can be used on the right-hand side of pipe operator. So let's implement it. And let's begin with the simple question. What is this toStr mechanically? And here's a minimal skeleton. We already have toString over any range as a plain function. Now we introduce a closure object, something callable, whose call operator simply forwards to string. And this call operator also forwards to string. And then we introduce this adapter object. Its call operator with range argument returns to string directly. Its call operator without argument returns the closure. And then we define the pipe operator outside. Pipe operator taking range and closure applies closure to range. And now you may say, stop here. Use to invoke here. And okay, you shall use to invoke here. It just not fit into the slide, yes? And the kegel is small enough already. So you may improve this, yes? And just be careful. To assert here is not constructing a string, it returns a closure. This is not an object constructor syntax. It is special call to create adapter to return closure, to participate in pipe operator, and to return something callable after participating in the pipe operator. Isn't this great? I mean, it's wonderful. Let me show you an example. This one, to string. This one, closure. This one, adapter. This one, pipe operator. This one is inline variable. And let's test it. And this, pipe to that, pipe to that. And you see everything works. Works like a magic. Except magic don't work. The ranges are. And in C++20 we didn't have a standard-based class for adapters, like view interface for views. So if you want to implement a real adapter closure, you don't want to hand-roll the pipe machinery every time. Instead, you derive from the range adapter closure of slice, like this case. And this is basically the same CRTP style helper that provides composition. Here's typical example, a slice adapter. Let me show you some code for this slice adapter. Yes. What is it? This slice adapter derived from range adapter closure of slice do have two variables, start and end, and substr start and end minus start. And that's all. I do have my slicer with start equals 1 and end equals 6, and it works from 1, from this element, to 6, to this element. And then I am doing drop 2. 1, 2. I'm dropping them, and this is 3, 4, and 5. And this is perfect. I just, like in lambda case, I just redefined a call operator. I'm no longer worried about all those pipe operators defined by myself and so on. Everything is hidden into range adapter closure. I'm just writing my logic, and everything works as if it is a real range adapter. Great. So it plays nicely with pipes. And this is a grown-up version of the toy skeleton we just wrote. And in C++23, we got something even nicer. We got ranges too. It's a general conversion adapter. Take any range and convert it to any container. Our toy 2 Esther was like a baby version of it, yes? Now we can write ranges colon colon 2 stud string, and that is fine. It will convert it to stud string. This idea existed in Ranges v3 library for a long time, and it finally made it into the standard. And if you look at the implementation at Ranges v3, let me show you. Let me show you Ranges v3 implementation. Like you see, it's a lot. It's here, and here some concepts, and here some unwrap function, and all our favorite C++ magic, like over there, and to container with function, with construct, and here, what is this? What is this function construct? We construct these inserters and then have some variants of how container may be constructed from a range. And we constructed our string from common view with pair of iterators, yes? But things are really more interesting because you do have some containers that are constructible from range and arguments, like here. And then you are just using this. Second, this. You have some containers that are constructible with special from range argument. And if this is the case, you are using from range argument and construct them. And only third attempt is what we try to announce to string. We just create common view, create begin end, and construct from begin and end. And if even this fails, we can reserve and copy ranges copy with back inserter. Just push back, push back, push back, push back, and construct. And only if everything failed, all if context here failed, we are calling static assert. This is nice. And here, what do we see here? We see some compositions, we see some requires clauses, and finally we see our beloved pipe operator. And you can see in the grown-up code, pipe operator is slightly grown up, and it heavily uses all compile time magic on all metaprogramming magic we saw earlier in this course. So everything now tied with everything else. Okay. And last but not least in this lecture, we need to do our own investigation of something goes wrong. We need to participate in little but interesting bug hunt. So it's always interesting when something doesn't work. And ability to handle with issues is critical ability for the computer programmer. So let's look at this example and let me show it you immediately on the Godbolt. And I hope you're here, yes. So let's look at this example. What I'm trying to do. Basically, here I'm trying to output prime numbers, but in like slightly interesting way. So what do we have? I do have something like concatenation, and concatenation concatenates two views. I will show you this function, and this is like test that concatenation works, and it works. Second, I'm concatenating two views, view single of 2 and view single of 3. And you need to recall that view single is view over the single object. And it is always borrowed, so nothing hangs here. No problem. Great. So first two primes, and I may output them. Let me, for now, comment out everything else and show you how this works in its simplest form. Let's do something like this. And you see concatenation works, and first two primes output correctly. Great. Now let's take a last step. I do have this modulo 6 lambda, which left only x modulo 6 equals 1 or x modulo 6 equals 5. Because if number modulo 6 not equal to 1 or 5, it is not prime. Everything that modulo 6 equal 0, 2, 3, or 4 are divisible by 2 or 3. First two primes. Great. And what are others prime numbers? And others prime numbers are use iota 5, 8, 6, filtered modulo 6, filtered by is prime function. And now I'm concatenating first two with others. And now I'm taking first 20 primes and I want to print out first 20 primes. Why not? So let me show you how this implemented. So is prime function is here. And that's great. It's very really naive. It's is prime function, yes. Concatenation. Concatenation. Let me make it even easier to read for you. So concatenation, we already sure it works. And we have concat view of v1, v2 is constructor of concat view of v1, v2. And concatenation view is something like this. We do have our parent view. We do have first and second iterators. And when first is done, second starts. And we have some iterator magic. And now we do have some constructor which constructs parent, first and second, and dereferencing. If not first down, dereferences first, otherwise dereference second. And operator plus plus, if not first down, increments first. If it ranges its end, it is done, and else it increments second. And this operator plus plus works in terms of previous operator plus plus, and this operator equals, and this operator equals, and everything else is like operator equals with sentinel, true only if first done and e second is sentinel. So we passed O first and e second is sentinel. Okay, this is simple part. And we have this concat view public view interface. And we have class iterator, class sentinel as forward declarations here. And implementation of sentinel class is really simple. Okay. And this don't work. And what it says? No matching function for call to concat. Let me rub this. Rub lines. Wow. What's the problem? Candidate this. Template deduction argument substitution failed. Constraints not satisfied. And what are constraints? Range of TP, view of V, TP-ref of T, and stud ranges CPO begin of T is invalid. And the required expression begin is invalid and end is invalid. What does it mean? And please click on this link. Download slides. Click on this link. Investigate this code. Pause this video and try to find the bug yourself. And this is first of two bugs in this code. So after you find this bug, the code will not compile. But please, right first, please look up the first one. 3, 2, 1. And let me show you how to think about this. You see this iterator. This is concat view iterator, yes? And this iterator have something wrong with begin and end. And if it has something wrong with begin and end, probably we are wrong with this category. And probably this is not stood forward iterator. And let's write static assert that this is indeed a stood forward iterator. How will we do it? We need some views to parameterize it, yes? We need some concat view to parameterize it. And it is simple because we do have our single views to parameterize it. So we do have like this one, concat of view single 2, and we have Jekyll type of this. So static assert, so using concat type is Jekyll type of this one. Great. And now static assert that looks like stood forward iterator of tag name concat type iterator. Tadam! And let's see if it works. Probably I need to include something like concepts here. Oh, it is already included. And let's look if this works. It's always interesting for me. Like, oh, static assertion failed. So basically, this is not forward iterator at all. It is not forward iterator because, and now let's see why is it failed. Weakly incrementable input or output input iterator. These requirements. Nested requirement is signed integer. Difference type not satisfied. So error messages leads us to error inside difference type. And let's fix it. What's the difference type in this concat type? It is interesting. And bingo! We see the error right away. This is stood common type, but remember Sphena lecture, we need to unwrap stood common type T. And this is error. And you see, everything is good now here. And first bug is found. This is no longer failed. Still, code does not compile. With other error. And other error is little more subtle. And if you failed to find first error, please pause the video now and show me the best. Like, try to find second error. 3, 2, 1. And if you just want to enjoy the show, let me just show you the result. So, what do we see here from the error message? From the error message, we do see here that this is concat of v1 refref, v2 refref, and is object v failed. And if is object v failed, what does it mean? It means somewhere we have offending reference because reference is never object. We also had this in these lectures. And let's check our concat function. And you see, yes, this is this. v1 refref, and here is v1, and if v1 is a value, then this is reference, and this shall not be reference. This shall not be an object. So to make this work, we need to like remove reference to here, but I'm lazy. I will do something like this. This will work anyway. And I will maybe I need to remove forward here and make everything a little uglier. So proper ways to remove reference here, yes. And this is like workaround, hacky workaround. But let's see. Yes, this hackish workaround works, and these are all primes. But feel free to correct this in normal way just with remove reference. It is good exercise. So yes, you see, ranges, in some cases, ranges can be scary, but please don't worry. With some practice, you will find out your way out of the subtlest bugs. So key lessons. Always verify that your iterator is actually an iterator. Check a view is really a view. Please go to this example and write static assert that your view is really a view. Never hesitate to check a concept and be cautious with overly qualified things. Overly qualified things end up not matching a concept. And little bibliography in two parts. First, I want to recommend you the fundamental talk of Eric Niebler, Ranges for the Standard Library. It is 2015, and it is really early inception of ranges. 3 talks of Tristan Brindle, 2019, 2020, 2021, and then I believe Tristan Brindle just got tired from ranges. And if you see those talks one by one, it is really interesting and it's really funny because this talk is rather naive. It is rather like Tristan Brindle finds out what ranges are. And this talk is much more complicated. And here Tristan starts to state some really worrying questions and find some really interesting answers. So just watch all 3 in a row. This time will not be lost. And also, I want to recommend you this Nika Yasutis talk of my favorite C++ 20 code examples on a Q conference. And this is talk where Nika blames ranges for constants lost for any other things. It is brilliant talk, I believe. Just to wait. It shall be like 2015, yes. And ranges algorithm in back-to-basics talk from Klaus at Gigelberger. It is very interesting to see ranges in back-to-basics session because I believe ranges are not basics in our language, but Klaus Gigelberger give a really interesting talk, and of course all other talks in this bibliography. And now we did it to the end of our first part of our course. We investigated systematically what can be done at compile time. In the second part of our course, we will investigate everything that cannot be done at compile time. We will investigate multithreading, allocators, and atomics, and GPU, and so on and so forth, and dynamic polymorphism, all things that are impossible or virtually impossible at compile time. And second part will appear on YouTube after New Year, I believe. So stay tuned. And that's all for today and for this semester. And goodbye.